Thanks very much. I have never seen a PCIe device look so delicious. So we spent the morning sort of learning, and some of the early afternoon learning about how you can take sort of the initial hyperscale innovations that are happening and applying them to sort of at scale, either cloud deployments or big data applications. But our next speaker is going to come up here and talk to you again how to take that back to the hyperscale level. Please help me welcome, well, first off, if you use an Outlook account or you have an Xbox or you use Bing, then you obviously know who I'm about to welcome up. Please help me welcome Kushagra Vaid, the General Manager of Cloud Server Engineering from Microsoft.
Thanks for the introduction, Cole. I'm pleased to be here and present to all of you. You heard the big news today in Bill Lang's keynote this morning about Microsoft joining OCP and also contributing our cloud server design specifications to Open Compute. So in my talk, I'll cover some of the details on what were the principles behind the design and what are the key features, and how do you design for an infrastructure of 1 million servers. At the end of my talk, I'll also give you pointers if you want to find out more information. There are technical tracks that are going on downstairs, so if you want to continue finding out more information, you can go there. So as you noticed this morning, Microsoft, you may not know this, but Microsoft operates about over 200 cloud services. The big ones, of course, are the ones that you know: Bing, Office, Windows Azure, Outlook, Xbox. There's several other ones that we operate as well. One of the key considerations in designing our cloud infrastructure was to address this challenge. How do you design a common architecture that can take into account the requirements of this diverse set of applications? Bing is a very compute-intensive workload. It's very heavy on the CPU. At the same time, something like Outlook.com, which is email storage, is very storage-heavy. There are some other applications that are network-heavy. So one challenge we faced when we set out to design this infrastructure was, how do we have a modular and flexible architecture that can take into account the workload variations that we host in our data centers? Talking about data centers, this was a second challenge that we wanted to address. Microsoft has data centers across the globe. There are data centers that are sort of what I call mega scale. You could look at them as 60 megawatts or larger in one facility. And on the other side of the spectrum, there are data centers which are essentially edge locations where you might have a few hundred servers. So then the challenge becomes, you're doing deployments across the globe. You need a supply chain to get these servers delivered to all these locations. And then you need to operate them across this spectrum of data centers as well. So how do we design an architecture that can take into account these set of parameters as well? So before we go into the design specifics, let's take a step back and try to understand the differences between the endpoints of scale. So what I have here is 3 columns that talk about a design that is optimized for maybe a scale of around 10,000 servers or so, a design that's for 100K servers, and then what I call cloud scale, which is a design that's optimized for 1 million servers. We'll walk through 3 elements here: design, supply chain, and operations, and see what differences exist in the scale as we go about designing this architecture. So on the design side, when you're deploying and operating 1 million servers, one key thing to keep in mind is that you cannot have a whole large number of SKUs. By SKUs, what I mean is variations in the BOM configuration of the server itself. At this level, the hardware reliability becomes less important, and the software is the key entity that provides reliability for the application. That allows us to make a lot of simplifications in the design of the hardware itself, so that the hardware availability can be somewhere between 99% to 99.9%. And the software does the load balancing and failure recovery and across availability zones. And so that helps a lot in keeping the hardware simple. The design that is done for the server is tightly integrated with the data center and the network. So this is basically a vertical integration scenario that you have to address to drive that level of efficiency in the design. So this is some of the factors that we had to consider so that we optimize this for a million server scale. Looking at the next big area where the optimization needs to be applied is supply chain. Essentially what this means is from the time you place an order for the servers to the time you have the servers up and running and online serving bits and serving traffic to end users, all those stages in the middle. So the key things here is what is the deployment size? And as you can see, for a big deployment, it's very inefficient to deploy in small chunks. So what happens is you deploy these large chunks of servers. In our case, it can be somewhere around 10,000 servers in one chunk that's kind of drop shipped and deployed in one instance. The ecosystem engagement model for how do you source components, how do you manufacture components, how do you integrate, assemble, and deliver components, that's very different as well. Direct negotiations with component suppliers, consigning components to the manufacturers, manufacturing the material, for example, the sheet metal and boards, that becomes a factor to consider. And finally, on the quality aspect, the warranty aspects, there's a lot of cost savings if you start looking at doing self-warranty in these scenarios. The last and most important aspect is how do you operate a fleet of over 1 million servers. So here, the operations model needs to scale with the number of servers that are installed. And we also have to keep in mind that in this case, the servers are deployed globally. So one of the biggest differences is what is the support model. And in contrast to a traditional IT enterprise environment, when a server goes down, you don't have to have a 24/7 staff to go replace it. In Microsoft's case, it could be sometimes from 1 week to 2 weeks before a server even gets replaced or serviced. So it's a model where it's very low touch, and the software that is operating the server, the infrastructure, takes care of ensuring that the workload can be shifted to a different part of the infrastructure if a particular server goes down. So that when the service availability is considered, the service availability requirements are met, and the end user doesn't see any impact. But at the same time, the service costs are kept under control. The issue triage model is basically based on instrumentation, monitoring, and machine learning algorithms applied on top of that. What this allows you to do is basically help to triage issues in an automated manner without a lot of human interaction. That makes a big difference when you're operating a large server fleet, because you don't have to have people go and look at every issue that comes up. The algorithms, of course, improve over time as new issues are found. Management out of band, there are instances when you still want to go and see what's happening in the server. One big difference here for a large server scale is the BMC needs to be either very minimal, or in fact, you can not even have a BMC. Essentially, what you need is the ability to turn a server on and off. So for example, in the instance where we operate servers, if a server has issues, the first thing we try to do is to reboot the server. A lot of times, you will not believe it, the server comes back up and it's fine. If it doesn't work after 3 times, then you schedule it for service. But the only functionality you need is just on and off, no BMC required. And finally, the FRU, or the field replaceable unit, in this case, is the entire server itself. So unlike a scenario in a typical IT enterprise where if a hard drive fails, you have hot swap capability, and the service technician will go and replace the server while it's running. In this case, you don't have to do that. If a server fails, you shut it down. When the technician comes a week or 2 weeks later, they will take out the whole server, they'll put a whole new blade in, and you're up and running. So as you can see, this is very different. It's a very different operations model from what you would see in a smaller environment. So the question then becomes, so when we started out this project about 2.5 years ago, the goals that we set for ourselves had to comprehend the principles that I just mentioned, but they had to be sort of inclusive of some of the design parameters and also the life cycle of the whole server. On the architecture and design aspect, we wanted to make sure that we ride the commodity curves so that our architecture would always get the benefits of the latest technologies while taking advantage of the commoditization that's happening in the industry. Feature simplicity was key. One example I gave you was the simple on-off methodology for managing servers. And it's important to keep in mind here that when you operate at a large scale, even the smallest issues that you come across can get really magnified. So simplicity of features, not putting any features which are not required, and keeping the infrastructure really simple becomes a key goal. Efficiency is always important. That kind of goes without saying. Power efficiency at that scale becomes a big deal. And of course, there needs to be a way to continue to innovate as this architecture evolves over time. For manufacturing and supply chain, how do we minimize the materials cost? And how do we have a model where you can do low-cost mass manufacturing becomes a main thing. Streamlined assembly, because that shrinks your PO to deployment cycle, becomes a factor to be considered. So that was one of the goals we wanted to use. And reuse of existing industry components. Things like power supplies, fans. We didn't want to necessarily go and reinvent the wheel unless there was some significant benefits from doing so. On the operations side, there were two key parameters that we set out to address. One was scalability, so that as we operate this large infrastructure, the systems management protocol would be scalable. And second was security. Security is something that's very important, as you would imagine, but unfortunately, there's not a lot of attention paid to it. One thing we want to make sure was that there were multiple levels of security defined in the management architecture, so that essentially it would be as close to bulletproof as possible from an operations standpoint. And finally, during the decommission phase, when the servers get retired 3-4 years later, how do you reuse to the extent possible? How do you upgrade the necessary components so that you reuse some of the materials? That becomes an important factor. So it really comes down to three things. You need to have standardization and modularity. You need to have design simplicity. And you need to really focus on sort of the operations aspect. So given that, let's take a look at the features of the Microsoft Cloud Server specification. The first one is essentially about how do we drive efficiency for power and for systems management and for the manufacturing aspect. So the chassis that we have designed has shared power, shared mechanicals, shared systems management, and shared cooling. What this allows you to do is to amortize the cost and power elements across the servers that go in the chassis. The chassis itself can take 24 servers in 12U. So it's a high-density optimized design, which is, given the range of data centers we operate, from large data centers to container-based data centers, becomes a factor. What we have found is that compared to traditional enterprise servers, this can give us up to 40% cost savings and up to 15% power efficiency benefits. And the power efficiency benefits are not just from using efficient power supplies. They also come from ensuring that the system is phase balanced, which is an important aspect to consider when you integrate the design with the data center. The second key feature in the design is for how the blades are installed and serviced. One interesting thing we did here was to get rid of all the cables that are in the path of installation and repair. So if you look at the picture here, what it shows is that there is a backplane which has connectors for signal transmission into the blade. What this allows you to do essentially is when the chassis and the blades are installed, you don't have to have any cables in that path to install or detach. And during operations, when the blades need servicing, it's the same thing. You turn the latch, you pull the blade out, and you replace the necessary components, and you push it back in. The big difference that we have noticed by having this kind of a design is the simplicity in the human operations piece. The human operations errors have gone down significantly, and errors that we had because of cables being loose, that resulted in no problem found, have pretty much gone away. And that also helps us to keep the availability up based on a design principle. We have seen up to 50% improvement in our deployment and service times based on this cable-free design, and this is one of the key features. The third key feature is how the supply chain aspect works as far as the system assembly goes. So if you look at the back of the chassis, which is shown here, what happens is the cabling for the network and storage components is done one time at the factory. So the configuration for the server is given to the manufacturer, and they would go and cable up the right the network storage cables in the back. And once that assembly is done, you would never touch those cables again, even for server installation and repair and whatnot, which is the previous point I made. So now this allows you to do multiple things. First of all, it allows you to streamline your assembly process. And in fact, you can start to do pre-assembly of the chassis with the pre-wired cables and speed up your installation process, which also helps with the deployment time. More importantly, it helps with cable reduction. And we did some estimates, and we expect to save about 1,100 miles of cable for an installed base of about 1 million servers. Lastly, but not the least, systems management is very unique in the Microsoft Cloud Servers solution. We have a management card that goes in the back of the chassis in the zero use space. The management card is based on a system-on-chip design, and it allows you to access the system through a REST API. The REST API supports an SSL protocol that helps with the security. So let me talk a little bit about the security aspect here. So there's 3 things here that contribute to the security of the infrastructure. The first one is the management card has a trusted platform module, what's called a TPM on it. So when you boot up the OS, the embedded OS on the management card, the boot is authenticated, and it gives you the assurance that there has been no violation of the golden code path that is running on the management card. Once that is done, the second thing is how do you set up an infrastructure where the commands that are received by the chassis management card can be attested to be secure as well. So in that case, we set up a certificate, a digital certificate, and help enable a SSL session from the management controller to the chassis manager, which helps to make sure that the commands are indeed coming from the right entity. Thirdly, it supports role-based authentication. So if you think about Active Directory-based domains where you can have users, operators, and administrators separated in different categories so that the right authentications are applied for people who want to manage the infrastructure. So this multiple levels of security give us a lot of confidence that the infrastructure is secure and protected from threats, internal and external both. And the REST-based API allows us to make sure that as the infrastructure scales, there are no bottlenecks that will be observed in operating this infrastructure. The chassis management card also supports built-in diagnostics and self-checks so that it's very easy to find out if something is wrong. And this helps with the machine learning approach that I mentioned earlier. What we are contributing as part of joining OCP are four main things. Of course, there are the specifications. There are 350 pages of design specifications that will be available on the Open Compute website, which cover the blade design, the chassis manager, the management protocols for the REST API to the chassis manager, and the mezzanine cards for network and storage that will go on the blade. Secondly, to complement these specifications, the mechanical CAD models in Pro-E format are also part of the contribution. This will be for the chassis, the blade, the chassis manager, and the mezzanines. Essentially, you can take these mechanical models and you can give it to a contract manufacturer. Everything you need to manufacture this is going to be available through this. The third thing is the board files and the Gerber files with the schematics for the chassis manager, the backplane, and the power distribution, the shared power distribution plane. So again, this is, if you want to take it to manufacture it, all the information needed will be available. The fourth thing is the source code for the chassis management. So the software that I mentioned, which runs on the chassis manager, which does things like fan control, power supply management, blade management for blade on and off, the REST API, security, all those pieces. We'll be putting it on GitHub, and we'll be working with OCP to have an open source project to work with the community on improving and enhancing the functionality. So that's the contribution from Microsoft to Open Compute. We are very excited on joining OCP and look forward to working with the community in advancing the design and sharing our learnings from our experiences at operating a million server scale. If you want to get additional information on the next level of technical detail, there are 4 technical tracks that are being presented today. It's on the lower level in room 22B. The first one is on the system architecture or hardware overview by Mark Shaw. Mark Shaw has been elected by the OCP community voting process to be the chair of the OCP server committee. The second track is on the management software overview. So this will cover the security mechanisms, the diagnostics, the management protocols. Badruddin is giving that talk. Badruddin will also represent Microsoft in the OCP management committee. The third talk is on the blade compute and the JBOD expansion. Martin Goldstein will be giving that talk, and Martin's also going to be our representative into the server management committee. The fourth and last talk is on the chassis manager, which is going to be given by Brian Kelly. Brian will talk about the details of how the card was designed and how the wiring is done, how the system is set up, and things like that. And there's a Microsoft booth on the floor if you want to see an operational system and learn more about it. You're welcome to join us at the booth, and we'll be happy to show you the system. Thank you.